we're launching thousands of new satellites into orbit, creating these incredible swarms that give us everything from global internet to pinpoint GPS. But have you ever stopped to wonder, what happens if one of them fails? Could a single glitch set off a chain reaction that brings the whole system crashing down? Well, let's get into it. So, to really get a handle on this risk, we first have to understand the sheer scale of what's happening just above our heads. We are, and I mean this literally, in the middle of a complete transformation in space. And this slide, wow, it just says it all. For the longest time, launching a satellite was this rare, monumental event. But just look at the last decade. The number of nanosatellite launches has absolutely skyrocketed. And if you follow that chart to the right, the projections show it's only going to speed up from here. We are truly living in a new space age. To put a hard number on it, researchers are predicting that nearly 3,000 nano and microsatellites are set to launch in just the 5-year period between 2021 and 2025. That number is it's mind-boggling. So what on earth is driving this explosion? Well, it pretty much comes down to one thing: money. Your traditional, big, school bus-sized satellite, that can run you hundreds of millions of dollars. But now look at this chart. A small satellite can cost as little as $100,000. All of a sudden, it makes way more sense to launch a whole fleet of cheap, small satellites instead of one giant, expensive one. Okay, so we have these huge swarms of little satellites whizzing around. But how do they actually coordinate to get anything done? Let's take a look at how they're designed to work as a team. The secret sauce here is a technology called satellite formation flying, or SFF. The best way to think about it is like a flock of geese, or maybe a team of synchronized dancers. Instead of one big, clunky machine doing a job, you've got a whole team of smaller, more nimble ones, all coordinating their every move to act like a single, incredibly powerful system. And the benefits of this approach are, well, they're huge. It's way cheaper, of course, but it's also much more resilient. You see, if a component fails on a single big satellite, the whole mission could be over. Just like that. But in a swarm, if one satellite goes down, the others can just adapt and pick up the slack. That's what we call enhanced redundancy, and believe me, it is a total game changer. This all sounds fantastic, right? But here's the catch. It introduces a brand new and, frankly, pretty scary kind of problem. What happens if the failure of one satellite doesn't just take itself out of the game, but starts taking its neighbors down with it? This is what engineers call fault propagation. And you have to remember, these satellites are all connected. They're constantly talking to each other, coordinating. So a single error, a bad sensor reading, a corrupted command, can cascade through the network like a virus. It's a domino effect, happening in orbit at 17,000 miles per hour. And listen, this isn't some theoretical what-if scenario. This table shows just a handful of real-world examples of small satellite missions that have failed. Look at Cutesy-1. It lost all communication after just 54 days. Or the AAU CubeSat, a total mission failure. The risk of losing these incredibly complex systems is very, very real. So how in the world do you stop a domino effect in space? Well, the very first step is just figuring out that a domino has even fallen over in the first place. Okay, this slide is actually really important because it highlights the two different ways engineers approach this problem. On one side, you have fault diagnosis. Think of this as being about the present. It's the alarm bell screaming that something is wrong right now. But then you have fault prognosis. That's about the future. That's the crystal ball trying to predict that something is about to go wrong. The diagnosis part is almost like a cosmic detective story. First, the satellite is constantly monitoring itself, comparing everything it's doing to a digital model of a perfectly healthy satellite. If something doesn't match up, it generates what's called a residual signal. That's your first clue. If that signal gets too big and crosses a certain threshold, bam, the alarm goes off. A fault is declared. And finally, the system has to play detective and isolate the problem. Which part, which sensor, where did things go wrong?
And here's the really clever part. This whole process isn't handled by one single brain in the sky. It uses what's called a distributed architecture. Basically, every single satellite is responsible for watching its own back and the backs of its immediate neighbors. This makes the whole swarm way more resilient because there's no single point of failure that could take down the entire monitoring system.
So we have a pretty decent handle on finding faults once they've already happened. But the holy grail here isn't just reacting to failures, it's preventing them entirely. And to do that, you have to learn to predict the future. And this is exactly where fault prognosis comes into play. The entire goal is to predict a component's remaining useful lifetime, or RUL. It's not just about seeing a tiny crack in a piece of equipment, it's about being able to calculate exactly how many hours or days are left until that tiny crack causes a catastrophic failure. It lets you take action before anything actually breaks.
And this is the crucial point of this whole discussion. While we've gotten pretty good at diagnosis, the what's wrong now part, this quote from the source research paper reveals the real massive challenge. The authors say that when it comes to fault prognosis for these satellite formations, there's a huge research gap. In other words, we are building these unbelievably complex swarms without a reliable way to predict when or how they're going to start failing. This gap, this difference between our ability to build these incredible systems and our ability to predict their failures, that brings us to the next great challenge of our modern space age. Because we have to ask the question, what are the real-world consequences of not being able to see these failures coming? I mean, what's really at stake here?
Well, the stakes are enormous. This is about the reliability of the global internet and the GPS services that, let's be honest, we all depend on every single day. It's about the success or failure of future scientific missions, and maybe most critical of all, it's about preventing these missions from turning into uncontrollable, hazardous space junk that could threaten our entire orbital environment for decades to come.
So the real takeaway is this. For all of our incredible ambitions in space to actually succeed, our satellite swarms need to become more than just smart. They need to become self-aware, capable of not just diagnosing their own problems, but of predicting their own futures. And that leaves us with one final, pretty provocative question. As we continue to fill the sky with these brilliant, complex networks, are we building a smarter, more connected planet? Or are we just creating the catastrophic space junk of tomorrow? The answer, it seems, depends entirely on whether we can teach our machines to see what's coming.